Okay, so welcome back to those who are watching. Um, in this lecture, we are going to continue with randomized rounding. Um, so we had seen last time a 1 over square root number of edges approximation for the maximum independent set problem. This time we are going to start off with the max set problem which we left midway last time. We are going to give a 3/4 approximation. Then we are going to go back to a problem that we have seen before, the price collecting Steiner tree problem. And we had seen previously using the primal dual method and deterministic rounding, the approximation. And we are going to improve this to a 2.54 approximation in today's lecture. And finally, we are going to look at the problem of congestion minimization in networks, in particular for routing integer flows in the network. And we are going to give an order log n approximation for this. And I may upload an extra lecture, which is a tree approximation for the facility location problem that we discussed earlier. Recall that we had last in the deterministic rounding part seen a 4 approximation for this problem. In fact, in class we had seen a 6 approximation, and I'd asked you to improve it to 4 in one of your assignments. We can actually give a 3 approximation for this problem if we use randomized rounding, and I might upload, as I said, an extra lecture on this one. Okay, so let's go on to the first problem of today's lecture, which is the MaxSat problem. Okay, so here's the definition of the MaxSat problem. We had seen this already in the last lecture when we got interrupted. The input is a set of n clauses on n Boolean variables. Okay. Now I'm going to introduce a slight generalization of the exact definition that we had seen last time. Every clause now can come with a certain weight. So clause Cj comes with a non-negative weight Wj. Every clause, as I defined previously, is the OR of some Lj literals. Okay, so clause Cj is the OR of Lj literals, and for instance, in this case, the literals are x1 or x5 or x1 or x10 complement. Okay, so a literal is a variable or its negation. The output that we want, as you would expect, is a 0-1 assignment for the n variables x1 to xn. And what we want to do is find an assignment that maximizes the weight of satisfied clauses. Okay. And notice that a clause is satisfied if any literal appearing to it is set as 1 according to the assignment. For instance, in the clause given over here, if either x5 is set to 1 or x1 is set to 1 or x7 is set to 1 or x10 is set to 0, the clause turns out to be 1. Okay, so first let us go on to see a randomized algorithm for this that does not use the linear program. And this is similar to the randomized algorithm for maxcut that we have seen. The algorithm is quite simple. For every variable xi, we introduce a coin toss xi, which is 1 with probability half and 0 with probability half. So capital Xi is a random variable and it turns out to be 1 with probability half. So we toss a coin Xi, and once it's tossed, we set the value of small xi depending on what capital Xi takes. So that's all that the algorithm is, and we'll see that this gives us a certain non-trivial approximation. So how do we go about analyzing this? Well, it is very similar to the max cut problem. That is, we consider a single clause Cj and we ask what is the probability that Cj is satisfied. So we'll actually compute this probability by looking at the probability that Cj is not satisfied, and Cj is not satisfied exactly when all the literals that is involved in the clause Cj take the value 0. Okay, and because every literal can take the value 0 or 1 with probability half, the probability of Cj not being satisfied is exactly equal to half raised to Lj, where we call that Lj is the length or the number of literals of the clause Cj. So this implies that probability that Cj is satisfied is 1 minus 1 over 2 raised to Lj. This implies, and I'm going to go over this a bit fast, the expected weight of clauses satisfied is summation over j is equal to 1 to m of wj times a random variable zj, which is 1 if cj is sat and 0 otherwise. So zj is the indicator random variable, and of course its expected value is going to be the probability that it is 1, which is in turn the probability that Cj is satisfied, and this gives us the following expression. That is, we have the sum of Wj multiplied by 1 minus 1 over 2 raised to Lj. Now, of course, one can simplify this in a trivial way, but this expression we'll keep in mind for later use. So the expected weight of clauses satisfied by a random assignment of 0, 1 values to the variables is exactly equal to, or rather is greater than equal to, the max, or rather I should say the minimum over j of 1 minus 1 over 2 raised to Lj times summation j equal to 1 to m wj, right? And since Lj is greater than or equal to 1, that is the length of any clause is at least 1, we get that this is greater than or equal to half times the sum of weights of all clauses, which is greater than half times the optimum. Okay, so this gives us a randomized half approximation. Just a random assignment to the variables involved. Now the point to note here is that in this randomized algorithm, the longer a clause is, the higher the probability of it being satisfied. Okay. In particular, notice the simplification that we did in order to get a proper approximation ratio. We took the minimum over here and we argued that since Lj is always greater than or equal to 1, we bounded the term here by half. Okay. Whereas if the length of every clause was greater than or equal to k, then you would get a 1 minus 1 over 2 raised to k approximate. So it is important, we'll use it later, that the actual weight of clauses satisfied is this expression here. Now, we will look at another algorithm, this time based on linear programming. So the first step, as always, is to write down a LP relaxation for the problem. So what are the variables that we'll use? Well, we're going to use two types of variables, one for every Boolean variable involved, that is the x1 to xn, and one for every clause c1 to c. So this gives us n plus m linear programming variables, which we'll call y1 to yn as the variables for x1 to xn, and z1 to zm is variables for clauses. And these take the natural meaning in the ideal setting that yi is 1 if xi is set to 1, and similarly zj is 1 if cj is satisfied by the assignment specified by the y's. Okay. Now the LP relaxation is quite simple to write out, especially the objective. The objective will have, we want to maximize the weight of the satisfied clauses. So this is quite simply the summation over all j of wj zj. Subject to the constraints, well, zj should be 1 if any literal in the clause is set to 1. So here we'll need some notation. So a literal clause cj is positive if it occurs as a variable. Okay, that is, it is a variable itself, and negative if it is negation of a variable. Okay. So when you have cj is the or of xi, I in the positive literals in cj, and an or of the negation of the negative literal. So I hope this is clear. So example, if we have cj is x1 or x2 or x3 bar, this denotes the positive part. Tj contains the variables x1 and x2, and nj contains the variables x3. Okay, so using this notation, we can write down the constraint for the above problem as the following. If any of the positive literals are set to 1, this sum is at least 1. And a variable in the negative part or the variable occurring as a negative literal in the clause Cj, if it is set to 0, then the corresponding literal is set to 1. So then this sum becomes 1 if any of the negative literals are set to 1. And if any of these turn out to be 1, then I want Zj to be equal to 1. Okay, so for every clause Cj, the following constraint should hold, that if any of the positive literals or the negative literals turn out to be 1, then the clause takes value 1. Now we of course want yi lies between 0 and 1 and Zj lies between 0 and 1. This holds for all I and this holds for all j. Okay, so I hope the linear programming relaxation is clear. Okay, so now we are going to go ahead and solve the linear program as the first step of our algorithm. We get the optimal solution, which is fractional, so the yi's and zj's may be some real numbers lying between 0 and 1. And the LP value of this is, we'll say ZLP, as is usual for us. Okay. Now we do the obvious thing. For every variable xi, we look at what yi is. We toss a coin which is 1 with probability yi, and depending on the outcome of the toss, we set the variable. And we output the resulting assignment. Okay, so let's go on to analyze this algorithm. Now the analysis is going to proceed in a similar way. We look at first the probability that a given clause Cj is not satisfied. So Cj is some fixed clause. So this is happening for a fixed j. What is it? Well, Cj is not satisfied when all the literals involved in it are set to 0, right? So look at the positive literals. What is the probability that a single positive literal I, which is involved in the clause Cj, is set to 0? Well, it is just 1 minus yi star, right? And because the coins are tossed independently, this is the probability that all the positive literals are set to 0. Similarly, what is the probability that all the negative literals are set to 0? Well, this is just the product of all the yi stars where the i's are negative literals. Okay. Now what we use is the AMGM inequality. This is the product of some LJ numbers, right? And so by the AMGM inequality, this is less than equal to the arithmetic mean of these numbers raised to LJ. Okay, here I've just used the following fact that the geometric mean is at most the arithmetic mean. And now we go ahead and try to manipulate this expression to get something like the LP objective value. Now we immediately transform this first of all using a simple thing. We write this as 1 minus 1 over Lj times summation I in Pj L star plus Mj star. Okay. So notice here that I have kind of in some sense flipped the way these terms yi stars occur. So I've brought it closer to a constraint in the LP. Over here, we had the PJs, the I in PJ, that is the positive literals occurring as yi stars, and the negative literals occurring, positive literals occurring as 1 minus yi stars, and the negative literals occurring as yi stars. We are just flipping that over because at this point, this looks closer to what we want. Okay, so here it's just an equality. Here it becomes an inequality, Lj. And what have we used here? That the yi stars are feasible. Okay, so if you look back at the constraint, we had that the sum over the positive literals of yi plus sum over the negative literals of 1 minus yi is greater than equal to zj, and that is exactly what we have used here. This is greater than equal to zj star, and so because all of these terms are negated, we get the following one. Okay, so this was the probability that Cj is not satisfiable, which means that the probability that Cj is satisfiable or is satisfied by this particular assignment is greater than equal to 1 minus j star by Lj raised to Lj. Okay. Now this is still not as good for us because recall that our LP objective value looks like a linear form in the ZJs, and here the ZJ stars are all trapped within this bracket over here. So here we'll use the nifty fact that the function is concave. Okay, so by concave I mean it just goes something like this. Okay, so it's like a bell curve. Okay. Well, the technical definition is that the double derivative is less than or equal to 0 for all x. This is concave in at least the interval that we are interested is x in 0, 1, and it is indeed concave in that. Now how do we use this? Well, we use a second fact, and this is easiest seen pictorially. Suppose I have an interval 0, 1, okay, and a function is concave here. It starts at a and rises all the way to b plus a. Then at any intermediate x, the value of the function is greater than or equal to bx plus a. So if f is concave and f of 0 is a, f of 1 is b plus a, and for all x 0 1, f of x is greater than or equal to bx plus a. Simple enough fact. How does it apply to what we have here? The probability, therefore, so let us consider the function 1 minus x by L whole raised to L. And this we'll look at as a function of zj star, which is in 0 1. Okay. Now what is f of 0? Well, notice that it is exactly equal to 0. F of 1 is equal to Lj. This implies that f of zj star for an intermediate point is greater than or equal to 1 minus Lj times zj star. Okay, so what I've managed to do using concavity of the function f is to pull the zj star outside this bracket over here. Okay. What this implies is that the probability that Cj is satisfied by a random assignment is greater than or equal to 1 minus 1 over Lj whole raised to Lj times Zj star. Okay. Now we can introduce new random variables and compute the expected number of clauses satisfied. So let me call that as Wj, which is 1 if clause Cj is satisfied and 0 if Cj is not satisfied. Okay. So, well, maybe Wj is kind of a bad terminology. So let me use Rj. Okay. So the expected weight of clauses satisfied is summation j equal to 1 to n of Wj Rj in expectation, okay, which by linearity of expectation is just summation Wj expected value of Rj, and the expected value of Rj is exactly equal to the probability that Cj is satisfied. So this is greater than or equal to, we'll just substitute this, the expression above, right? Now notice that the term over here looks very close to our LP value, except for the multiplying term here, which is different for every clause Lj, because the length of every clause is different. So what we are going to do is Like we had done in the previous randomized algorithm, we are going to just take a minimum and say that this, the quantity above, is at least this. Here